como vem sendo habitual, 2 apresentações. O que não é tão habitual é termos um convidado como o professor Jean-Pierre Bourguignon, matemático ilustre e atualmente presidente da European Research Council. Isso para todos os que têm ligações com a academia sabem o que é que isso quer dizer. Bien, Jean-Pierre, j'ai promis de ne pas prendre longtemps à présenter parce que tout le monde connaît déjà. Donc, c'est à vous la parole. Merci.
Merci beaucoup pour cette invitation et l'honneur que vous faites en faisant un nouveau membre. Donc, je vous remercie de l'invitation à donner une conférence sur mon sujet, qui est la géométrie. J'ai choisi de donner une conférence historique. J'aurais pu donner... Ça évite d'être trop technique. I will switch to English because I know some of you will be in trouble with French. So the title of my conference is A Brief History of Geometry. And actually a subtitle was already provided to you, which is From Euclid to Perelman, via a few number of people. I could have actually listed more, of course, because the genealogy is pretty long. And actually, I see this conference as really a pretext to show something about mathematics, which is my field. So mathematics as a machine that creates concepts and solves problems. How the geometry has evolved from being one geometry to many sorts of geometries. And this was a long process, a complicated process. How the philosophy behind the mathematics has actually evolved, its relations to the natural sciences in particular. But I could also discuss the relation to philosophy, but I will focus more relation with physics. And still to show that although geometry is one component of mathematics, there is a remarkable unity of mathematics. So I will show a few documents of historical importance, and even more important for me, because I really believe science is made by people, a nice gallery of portraits, so key people who made things happen. So I'm start with the antiquity, and of course the study of space has been really present in many, many civilizations. You can find trace of this in Egypt, Mesopotamia, China, and actually even for China, it's almost sure that the Chinese knew the Pythagoras theorem before Pythagoras ever existed. There's a drawing whose original date is still being debated, which contains in itself a proof of Pythagoras' theorem, one of the many different proofs. And this document, if the first origin is indeed true, was produced 900 years before Christ, so much before Pythagoras. Anyway, so this is just to show that the Chinese had already a very good understanding of geometry. And actually I will say a few words about the Greek contribution, because it has been a contribution which has had a long, long influence. Also because it provided a number of viewpoints, and in particular for mathematicians, it has provided a model of intellectual creation. And so you know this famous painting, which is supposed to represent the academy, so a good place to quote here. And in particular, you see Aristotle and Plato. Of course, they didn't live at the same time, but they're on the same painting. So that's what art allows, not reality. And you know that the statement, which is well known as more or less the title under the painting, is nobody should enter if he's not a geometer. So that was really some to emphasize the very central role played by geometry. So, of course, the key document for mathematicians altogether, but in particular for geometers, are the Elements of Euclid, which is probably the non-religious book which has the longest influence in the history of mankind. It provides a model of space, as you know, and a method to analyze it through the axiomatic method. So really you build your concept of space piece by piece, and you detail the relations of the various pieces with one another in a very axiomatic way. And a very interesting point, which actually played a very, very critical role in the whole history of mathematics, has to do what is usually called the Fifth Postulate. sometimes called the parallel postulate, which says the following thing. Really, in Euclid, we don't have any copy of the origin. We have only copies of this. But it looks like the statement was the following one. If you take two straight lines which intersect a third one, while forming internal angles whose sum is less than a flat angle, then they intersect on the side of these angles, provided one extends them far enough. Which, of course, immediately raises one thing, which is the far enough, which means that you have to push, you may have to push up to infinity almost to get the intersection. Of course, usually this is not the way it is stated, although it's fully equivalent. An equivalent statement is to say from a point which is not on the line passes one and only one parallel to this line, which actually is strictly equivalent to the longer formulation which is in Euclid. And another one, which is actually something I'm sure you learn in secondary school, is in a triangle, angles of a triangle sum up to a flat angle. So this is the same, all these are the same statement. And of course, as I already underlined, this is the only postulate in the elements which involves in some way infinity, because there is the far enough, which of course. So now, what has been really remarkable, this was in Euclid's Elements, so before Christ time, and this Euclidean geometry has survived many scientific revolutions, which is quite extraordinary. It was not touched. And as you know, there have been many revolutions concerning our understanding of space. Of course, there is the contribution by Galileo Galilei. He has this famous essay, Il Saggiatore, in which says a number of things on how one should understand the world around us, in particular the universe, and in particular his statement that the great book of the universe is written in the language of geometry. And he really specifies what he means by geometry. And of course, the great discovery, scientific discovery of course, Galileo Galilei, is that the state of rest and uniform linear movement are strictly equivalent from a mechanical point of view. This is very non-evident in some way, but it's really the basis of all modern physics. And of course, that's a great contribution. Another great contribution I'm sure you heard about and you are aware of, but I want to put it in the context of the geometry, is that of Johannes Kepler. So Kepler proposed very precise laws for the motion of planets. And planets were really errant in a sense. And so he really proposed, purely based on experimental evidence, that they move along ellipses around the sun, for which the sun is one of the foci of the ellipse. And it's very interesting because the usual way one gets to ellipses in geometry, for the Greeks, was definitely through the definition as we know, quadratic, the intersection of a quadratic cone with a plane. And this is the way you generate ellipse. You can also generate them differently, but this one is interesting because only one of the two foci plays a role in defining it. And the second law of Kepler is the segment between the sun and the planet sweeps equal areas in equal times, so it relates the motion as a geometric motion with a trajectory in time. And the last but not least, very important for astronomy, is that there is an algebraic relation between the length of the large axis of the ellipse and the period. So these were the three laws by Kepler. Another great revolution, which today it's very difficult to accept this was a revolution, was due to Rene Descartes. What Rene Descartes did, he proposed what we now call analytic geometry, which is almost an evidence. Every kid playing with video games is using coordinates. And so the key point, which was a very, very strong statement, there is even a quote by Hermann Von Helmholtz saying that this was an act of violence, which was to say that numbers on one hand and geometric figures on the other hand are really objects which belong to the same world. So claiming that you can translate geometric figures into numbers, or that any numbers can have representation in terms of figures, was a very very important breakthrough, because all of a sudden the figures you could consider became a much larger quantity. If you give yourself in the plane an equation which is a polynomial, then you get a curve which is worth being studied, and for which it's sometimes very difficult to come up with a geometric definition. You get it just purely as numbers. And also, if you think of this as a dictionary, it provides you also with a systematic analytic handling of geometric problems. A figure which is extraordinary is that of Isaac Newton. So as you know, Newton has done many different things, not all scientific, by the way. He was also somebody who believed in non-scientific things, but of course he's remembered for his scientific contribution. And one of his extraordinary contribution was the writing and the publishing of the book which is called Philosophia Naturalis Principia Mathematica, 1687. This is one frontispiece of one of the copies, not the eldest one, by the way. It's very interesting because the way it's structured mimics the Euclid's elements. So just to show you one page, you see that he very carefully introduces definition and statements in a way which really mimics the Euclid's elements. And of course, why is this document so extraordinary? Because in one document he does three different things, and which is not so frequent that one book contains. First of all, he is one of the creators of differential calculus, which of course now is for young students sometimes a nightmare, but is definitely a fantastic breakthrough for science. And he was not the only one. Actually, the first person who really came up with a precise definition for a differential calculus is a Japanese, and Seki Takakazu. But of course, Leibniz and Newton have been proposing some kind of competing definitions and different approaches. And also in the same book, something which qualifies him more as a physicist, he states the fundamental law of mechanics, which of course has been so decisive for the development of industry. So introduction of forces and the connection of the forces with the acceleration of the body. And of course, in order to make sense of the fundamental law of mechanics, you need the concept of acceleration, which is highly non-trivial. It's the speed of the speed. So if you don't have a good definition of differential calculus, there is no way you can make sense of acceleration. For a long time, people believed the motion was only connected to the speed, but not to the speed of the speed, which is very important. But also at the same time, in the same book, he describes the law of gravitation. So how bodies attract themselves. So what is the force created by inert bodies? And of course, what is extraordinary is that through these three main achievements, Newton was able to get in a completely deductive way all Kepler's laws. And so it's quite extraordinary that in this mathematical setting, with the two basic breakthroughs that he made in mechanics and description of gravitational interaction, Newton was able to recover fully Kepler's laws. Of course, even among, one good example why this geometry, this Euclidean geometry, was the setting that everybody accepted. If you look at the book by Immanuel Kant, Critic of Pure Reason, which is considered one of the really cornerstone of philosophy, states very, very explicitly that they are among the really absolute is the truth of Euclidean geometry. So this is very significant. And so both for him, geometry, Euclidean geometry, and Newtonian physics are a priori truth. And in a sense for him, there is no point in discussing space and time, because space is described by Euclidean geometry, and the connection between space and time is exactly incorporated into Newtonian physics. And so the end of the 18th century has been really the starting point of, discovery, or I don't know how to call it, or the creation, or that really Euclidean geometry should not be considered as the only geometry. So that's the emergence of new geometries. Probably the first person who really conceived that well, although he didn't publish it in a way which would be acceptable today as a publication, is Carl Friedrich Gauss. So Gauss, was a very talented mathematician very early on in his career, did many different things, both in number theory but also in geometry. And one of his key publications is an essay which is called Disquisitiones Generales circa Superficies Curvas. And this essay is very remarkable in that he really kept it in his drawer for 30 years. He was not happy with the final formula, and he waited until he got really the right formula for him. And so you see, we have to be patient and not publish too quickly. So the motto of Gauss was pauca sed matura. Few things, but things which are mature. So this is a very typical example. And actually, what is really remarkable in this essay is that he introduces the concept of intrinsic curvature of a space. So what does it say? Imagine you are considering as a geometric object this brown surface. So at the point of the surface, it's a smooth, nice, regular surface. At the point of a surface, you have a tangent plane, so this is a very simple notion. And of course, you have a normal to this tangent plane, which is a normal to the surface. And then you can imagine you take planes which are containing the normal and you rotate them. Of course, they cut the surface into a curve, and you can look for curves at the notion of curvature. This is a well-known notion, which is exactly the radius. Well, the curvature is the inverse of the radius of the curvature of the circle, which matches with the curve in the most optimal way. If they are very small circles, they are on one side of the curve. If they are very large, they just encompass the curve. And of course, there's a transition between the two regimes, and this gives you exactly the radius of curvature of the curve at that point. And of course, the inverse of this radius is the curvature. And so now, if you rotate, if you take these normal planes and rotate them, you will see that the value of this curvature varies between two extreme values. And the extraordinary statement that Gauss made, which is called Theorema egregium in the essay, is the fact that if you take the product of these two numbers, you can actually get at this number without thinking of the surface as living in three space. So here is the famous formula that took him 30 years to come with a good definition. So I'm supposed to push something. Yes. So you see the key point is you have the metric in the Euclidean space, three orthogonal coordinates. Then it induces on the surface, which has only two parameters, some functions, because of course the surface is curved, E, F, G. So these E, F, G are pure functions of P and Q, the parameters on the surface. And then you can create this number K, which depends purely on E, F, G and derivatives of E, F, Gs, nothing else. So it's purely computed on the surface, and this number K is exactly the product of the two principal curvatures. And this is what Gauss proves. And so he really wanted to get this formula. It took him 30 years to get it. He had other ways of getting at the number K, which were fine, but he was not happy, so he waited a long time. So this is the first time in history people understand that the space can be curved by itself. Not because it's sitting in another space, just by itself it's curved. Very important. Of course, now this led to new geometries for the reason that people understand then maybe there exist spaces which are not flat as Euclidean space, but which are curved. And I will give examples. So the first person who pointed to that was Nicola Lobachevsky, who was living in Kazan. He was even the rector of the university there. There is a very interesting report. So this is one of the papers he published on the theory of parallel and also the first essay on this, and you look at the title that he has taken, he called it Imaginary Geometry. To be very careful to not to pretend that this was a real geometry, it was something you can dream of. And it's very interesting because there was an inspector for the state which came to visit University of Kazan and really concluded that really one is wasting the taxpayers' money by paying people to do such work as this Lobachevsky's man, really creating these totally crazy geometries. Anyway, so of course that's an interesting feature. So he published several versions of his Lobachevsky geometry, which now we tend to call it hyperbolic geometry. But another person also, almost at the same time, slightly later, also discovered these new geometries, these non-Euclidean geometries, Jnos Bolyai. So Jnos Bolyai was the son of a mathematician. He was a soldier by himself. He was bothered not having much to do as a soldier. So he asked his father to provide him with some problems. So that's one of the problems that he solved. So he never published actually his work. It was purely an appendix of a paper by his father. So he's not a professional mathematician in some way, although he did a very remarkable contribution to mathematics. And so this new geometry is called hyperbolic. And of course, it's not Euclidean geometry because it violates the fifth postulate. The big debate which has been going on for centuries, or even more than a millennium, is whether the fifth postulate can be derived from the previous one without, as a proof, as a theorem. That is, can you prove the fifth postulate from the previous ones? And many people believe they had a proof. All the proofs were wrong. And actually, it's just the fact that you need the fifth postulate to get Euclidean geometry. If you take it out, you may have other geometries. That's exactly what. So in this hyperbolic geometry, if you take a triangle, and if you sum up the angles, then you get less than the flat angle. So in a sense, the hyperbolic geometry is a meager geometry. So the triangle tends to be meager. And also, it took quite some time for this new geometry to be accepted. And it's only when people could describe it in terms of a Euclidean model in some way that it became accepted. So here is a typically Euclidean model. So this Euclidean model, so the space is the whole interior of a disk. The notion of distance, you have the feeling it gets smaller and smaller, but actually it's not. In this metric, in the way you measure the distances, you still, all the basic figures have all the same size, but of course your instrument to measure decreases when you get close to the boundary. And of course, if you look at the violation of the fifth postulate, it's very obvious. If I take a point at this one, which is outside the line, so for me the lines are arc of circles which are perpendicular to the circle which is the boundary of this my space. And then you see I have many, if I take this point here, I do have many lines which, and I take, so this is my line. From this point I have many lines which do not cut this line, so they are parallel. So I have many parallel passing through this point to this line. So definitely the postulate, fifth postulate is violated. And actually, when people realized that there was the possibility of having these geometries, people realized actually they knew a non-Euclidean geometry for many, many years. And that's the so-called spherical geometry. So imagine you think of space as the surface of a sphere, just the sphere. And then for you, the shortest path, as you know, on the sphere are great circles. So it means the straight lines on the sphere are just great circles. And of course, as soon as you look at the triangle, it's obvious that the sum of the angles actually is more than a flat angle. And actually, you can even measure how much the excess, when I add up these three angles, the excess is directly related to the area of this. So in a sense, people had been using, using a non-Euclidean geometry, but they never called it a geometry. And at this time, it was clear that we had actually these two, in a sense, symmetric. So the Euclidean geometry is the space with curvature 0. The sphere is a space with positive curvature. And the hyperbolic geometry is a space with negative curvature. And actually, trigonometry has been developed, as you know, by astronomers to really do a number of calculations needed for them. And for astronomers, so you know the basic formula of trigonometry, which is taught in secondary schools. So these are the lengths of a triangle, and alpha is the angle opposite to the side A. And actually, it was known to astronomers that in spherical geometry, the analogous formula exists, but it has this formulation. Instead of, if you remember the expansion of cosine, it's 1 over a squared over 2. So if you look at the first expansion, if imagine a, b, c are small, you will see that you get a perturbation of this. So it shows that actually people have been, without knowing, dealing with non-Euclidean geometry. And actually, I will pass through that. There was also another geometry which people have been looking into, which is the so-called projective geometry. And of course, very important for artists because it is the basis for, as you know, is the basis for to handle perspective, and which is a very nice piece of mathematics, and which was actually, from a mathematical point of view, a very great contribution from Rene Descartes. So I move on, and of course, develop further in the 19th century by Poncelet, and well, it's very well known that projective geometry is a very nice piece of mathematics. So now let me come on to other major steps in the broadening of the concept of geometry. And of course, the next step happened in the middle of the 19th century and is due to Bernhard Riemann. You know, Bernhard Riemann has contributed to so many different parts of mathematics. Unfortunately, his life was very short, and a large part of his life he was sick. He was suffering from tuberculosis, which really weakened him a lot. But in spite of that, his contribution is absolutely extraordinary. So really, also what is quite extraordinary is that the domain of geometry that Riemann has created, which is now called Riemannian Geometry, was an interesting exercise. It was purely on the occasion of his thesis defense at that time in Germany, and it had existed for a long, long time. The candidate would present his work, but then also the faculty would offer 3 possible topics of interrogation, and just about 1 week or 2 weeks before the defense, then the candidate would know which topics the faculty had chosen. And Gauss was in Riemann's jury, and to the surprise of everybody, he was asked to speak about on the assumptions on which geometry is based. And so more or less his document has been produced within 1 or 2 weeks. Of course, probably he thought about it. At that time, he was really, for himself, thinking a lot about physics, in particular the theory of physics which was fashionable at the time about ether, which is really the underlying, structure on which all phenomena are based. And of course, you cannot do that without having a reflection on space. And that was, it's very interesting that this document was not published during his life. It was published after his death. And here is the document on the assumptions on which geometry is based. It's very remarkable. It's a piece of geometry without any drawing, 0 drawing, and also only 1 formula, and no explanation how you get the formula. The formula is completely correct, and you have to think quite a lot to get this formula. So this new geometry really has very extraordinary features. It actually, in a sense, it's a vast generalization of the contribution by Gauss, and it uses what I call the variability of the line element. You remember I showed you dx squared plus dy squared plus dz squared equal something which was written on the surface with dp squared, dp dq, dq squared. And the coefficient E, F, G were functions, so that's the variability of the line element. And of course, in this geometry, you have to know what replaces the straight lines, and they are the shortest paths, called geodesics. And it's through the study of the behavior of the geodesics of the shortest paths that Riemann comes up with an absolutely critical new invariant attached to this, which is the curvature tensor. So it's a generalization of the curvature of Gauss, the function k, which I showed you, which is a much more complicated object, which is a 4-order tensor. So it's still something which is very, very complicated, and but that clearly Gauss fully understood without having the tools to understand it, actually. Another person who contributed greatly, so we are still in the middle of the 19th century, slightly later, is Hermann von Helmholtz. So Hermann von Helmholtz is somebody who had a very interesting life. Here is the stamp which the Germans dedicated to him. And what is very remarkable, you see, that you see this eye. And the reason is that Helmholtz was really a medical doctor for almost all his life, and really invented almost all the basic instruments of ophthalmology. And he turned to physics when he was 60, and mathematics when he was almost 70, and with contributions which are really extraordinary. So there is time to do things. You see that you can have different lives. And so in particular, one book he published, which of course you remember the title of the book by Riemann, on the assumptions on which geometry is based. So the article by Helmholtz on the facts on which geometry is based. Very interesting. Remarkable article in which he discusses all kinds of models, geometric models that can be used to describe many different things. And I really, for a reason which for me is really difficult to understand, why this article has been missed for a long time. Actually, it was available, but people didn't really stress. In particular, in one thing he recognizes is the importance of spaces in which isometries, that is transformation which preserve distances, act transitively. And as I said, has been greatly ignored. And people tend to quote more another person, Felix Klein, and who was, of course, a great mathematician, through his so-called Erlangen program, in which he discusses in particular exactly what actually Helmholtz had been discussing before him, which is this fact that maybe you can turn things around and define a geometry as the set of properties which are invariant by a group of transformations. So all of a sudden, you take an approach in which something which was very concrete, very practical geometry, and it becomes an object of algebra. And that's a very big switch, an extremely important switch. And of course, this has led to very many relations between algebra and geometry. And of course, after you have given this definition, it's clear that there cannot be a unique geometry, because anytime you come up with a group, you have a geometry. So there is abundance of geometries. And of course, this has been extremely important in the further development of geometry. Another person I want to quote is William Kingdon Clifford, because you may know he had a very similar life to Riemann. He was also a genius. He died in Madeira, and I participated in a conference where finally somebody who was looking for that could identify the house in which he died, because he had a very precise description of what you could see from the house, and it was really fantastic. It was a conference dedicated to Clifford, and Clifford had been doing many different things remarkably. In particular, one thing which is amazing, he had a short article called The Space Theory of Matters, 1870, in which he describes exactly what will be the underpinning of general relativity, which is completely unbelievable. But this note is fantastically visionary. Of course, you can quote many other people. Somebody who played a very important role in this relation between groups and geometry is Sophus Lie, a Norwegian mathematician. And of course, there is the big work by David Hilbert, who really more or less took up the work done by Euclid and wrote his Grundlagen der Geometrie, very important look into the axiomatic approach of geometries. And so now I'm coming to a contribution which really should be considered as philosophically a turning point, which is the contribution by Henri Poincaré in a series of books which were really designed for a very wide public, I was very pleased that publisher decided to publish these 3 books. I was asked to write the preface, and my only condition, I didn't want to be paid, but I wanted the book to cost less than 20 euros. And it's for sale in 19 euros with the 3 books of Poincaré. I'm very proud of that. Anyway, so Henri Poincaré really, among his series on La science et l'hypothèse, there are 3 books in this same spirit. Here is the statement by Poincaré, translated into English. Geometric axioms are neither synthetic nor a priori statements nor experimental facts. They are conventions. What should one think of the question, is Euclidean geometry true? It doesn't make sense. A geometry cannot be more true than another, it can only be more efficient. So it really is very, very important from a philosophical point of view, because this statement claims the total independence of mathematical construction versus natural sciences, which doesn't mean there is no relation between the two. Exactly, his last sentence says that mathematics can provide models of a huge variety of models to really deal with representing the world. But it's not the world which dictates the content of mathematics. So now I'm coming to the part which is maybe more exciting, which is the early 20th century with contribution by great physicists. So 1905, you know, in physics, the so-called Annus Mirabilis by Einstein with 3 major papers. And this is a portrait of Einstein, supposed to be 1905. And Einstein really, in one of his contributions, which is about what one now calls special relativity, really challenged the postulate that space and time are absolute things. And he showed through his construction that actually you have to consider a space-time, although the expression is not from him, the expression is from Minkowski, mathematician who was actually the teacher of Einstein at the ETH in Zurich at some point. And another person who also took up the approach by Einstein was Poincaré, with a very different approach. Poincaré was very much focused on the theory of invariance of groups. And so in a sense, what Minkowski showed is that the underlying geometry, which really allows you to discuss space-time, is a new type of geometry which has what mathematicians called signature minus plus plus plus. So the key element is that the vectors of length 0 are exactly the vectors which are along the light cone, if you want. And so minus corresponds to the direction of time and plus corresponds to the direction of space. So these new type of geometries had not been very much studied by mathematicians, became really the very basic setting in which one should discuss physics. And so this was 1905, that was special relativity, which was very important to unify, to give a very good setting for electromagnetism, and really solved a number of problems. But very soon Einstein was unhappy about what one can say about the theory of gravitation. And he was really stuck for some time. But then in 1913, and with the correct equation 1915, he really created the theory of general relativity, not special relativity. And he was greatly helped by his friend and colleague at the ETH Zurich. At that time, in the 1910s, Einstein was a professor at ETH. He moved to Berlin later on, who was Marcel Grossman. So Marcel Grossman was a mathematician, very much aware of the research done at this time, and a very good friend of Einstein. So Marcel Grossman really introduced Einstein to a contribution to geometry, to Riemannian geometry, which had been done by Gregorio Ricci Flow, an Italian mathematician who had been, actually, in my opinion, really undervalued, who introduced in 1904, for strictly mathematical purposes, a piece of the full Riemann curvature, and which he wanted to use it as to do geometry with. Nobody has done any good geometry with that, but you will see that for physics it has become very, very important. So now the key element in this new approach to the theory of gravitation is that the Lorentzian metric, which describes the geometric structure of space-time, is purely determined by the position of matter and other physical fields. And of course, to get the fields equation took some time. As I said, there was two very interesting papers, 1913, unfortunately by Einstein and Grossman, unfortunately incorrect, and grossly incorrect, actually. And so anytime I quote this, physicists say, no, you don't have the right to quote this paper because it's wrong. Well, it has been published and under the signature of Einstein and Grossman. So anyway, but the true field equation appeared 1915 through a very interesting competition, cooperation between David Hilbert and Einstein. So the equation is this marvelous Einstein equation, which on the left-hand side contains purely geometric quantities, so this Ricci curvature and scalar curvature, which is a trace of the Ricci curvature, a piece of the Ricci curvature, times the metric. So this is the left-hand side, purely geometric, which describes, in a sense, how the gravitation functions. And on the right-hand side, you have the so-called stress energy tensor, which contains all the physics which is non-gravitational. So if you have electromagnetism, if you have all kinds of other fields, you have to describe them through T. And to solve the Einstein equation means finding G, that is the Lorentzian metric, which is determined by this. So the physical fields should determine the metric through its curvature. And of course, these new models have been fantastically successful, and you know now, even now we have evidence that one of the predictions of the Einstein equation, the existence of gravitational waves, now seems to be pretty well established, but also many other features which were very interesting features, like notion of black holes and so on, were discovered. So here is Einstein writing the Einstein equation of the vacuum. When there is no physical fields, the equation is purely that the Ricci curvature is zero. And now I want to move on to a geometry inspired by general relativity. That's my own reading of that. Some people will say geometers thought by themselves for that. I'm not exactly convinced. And one of the reasons is that if you look at the Einstein equation in a four-dimensional space, in space-time, the field equation, the Einstein field equation, can be viewed as a dynamic equation telling you how the metric induced on space hypersurfaces, three-dimensional objects, evolve a long time. So in a sense, you can read the field equation, the Einstein equation, four-dimensional Einstein equation, as some kind of a dynamic evolution equation of a family of three-dimensional metrics. Very interesting approach, which usually is called the ADM approach, Arnoville, Deser, Missner, the three physicists who proposed it. And it's very interesting to see that the leading term of this dynamic, so I'm telling you it's how the metric deforms itself, is exactly given by the Ricci curvature of the three-dimensional space. And this led a number of people some people, to use mathematically the idea of deforming the metric in the direction of its Ricci curvature. I didn't say, but I should have said that the Ricci curvature is mathematically an object which has the same nature as the metric. It's a symmetric two tensors, so it's a very similar object. So if you do that, then, the first person who used it was Thierry Aubin in an article in 1970. I myself, I really considered this question in a conference in Berlin, and one of the, that's from the proceedings of the conference, was to say, why don't we not just deform infinitesimally in the direction of Ricci, but why don't we try to have a continuous flow using this, which now is called the Ricci flow, for very good reasons, because you want to deform the metric through its Ricci curvature. And the person who proved that actually such a flow does exist, at least locally in time and space, is Richard Hamilton. And using he obtained some beautiful geometric results. But he had to make some curvature assumptions in order to get the flow going long enough. The first result he obtained was just for a short time existence of the flow. And then around the turn of the century, Grigori Perelman, a genius mathematician, I like this picture because you see Perelman next to Ricci curvature positive, which is similar to Einstein's picture in the sense, which was looking at the Einstein equation. And what Grigori Perelman showed, that you don't need these curvature assumptions, but the price you have to pay from a mathematical point of view is considerable, because this flow may develop singularities. It may not be smooth. And then from that on, he showed the very extraordinary fact that if you start from a three-dimensional space, assume it's closed, compact, as we say, and assume it is simply connected, which means that any curve you draw on it can be shrunk to a point. Then if you are in such a space, imagine you put any metric, you start to deform by the Ricci flow. Maybe the space is going to squeeze itself at some point, and then will develop a singularity, the flow will stop. But he can show that the piece which goes out is still a sphere, and you are able to continue the flow on a new object, which is the space you started with a sphere taken out, and you continue. But the key thing is that you can do that only finitely many times. And when finally you get a space on which you can let the flow go to infinity, then finally you get a true round sphere. And then from the topological point of view, if you have a sphere to which you add spheres, you still have spheres. So this was the solution of the famous Poincaré conjecture, which is to say that if you have a three-dimensional space, compact, that is closed, simply connected, the only possible space is the three-sphere, nothing else. And that was a very indirect proof, because of course it looks like the Poincaré problem is a purely topological problem. It has nothing to do with metric. But using this trick of using the metric and the flow, you can solve that. So this was a wonderful success for modern geometry, and its combination with nonlinear partial differential equations and inspiration from physics. Maybe I should stop here. I have some more developments, but maybe that's already enough, and I'm willing to say more on this. I could talk about the work of several other people, Alexandrov, Gromov, Kohn, and a few others. Thank you very much.
Thank you very much, Professor, for your excellent talk. I'm just now going to ask the audience, anyone would like to ask a question? If you want, please.
Okay. Merci. It was a great pleasure to see the whole puzzle of this geometry. I have just two small comments. It's very difficult, but it was a very nice way to get this flow, the history of mathematics around geometry, and finalize with the shape of the space finally. In fact, I have two comments. One is that I was very pleased to see the importance of Gauss and Gauss for what is now called non-Euclidean geometry. In fact, that's a 19th century concept, of course, because the non-Euclidean geometry was not very basic. I mean, spherical geometry, even that now geometry was known since antiquity, was taking a crucial role in discrete geometry, discrete mathematics, before the Descartes and Newton revolution. In the 16th century, the revolution of the Europeans get out of Europe to the seas. And in fact, cryptography, I think, was something that I missed. I mean, the cryptography since the Greeks, like Aristotle said, was first introduced non-Euclidean method, and then in the 16th century, where the first projection starts to appear, and that was crucial for Gauss, and for Gauss to reach the non-Euclidean geometry. And in this process, there is a Portuguese mathematician that I love to study.
Please.
Because Pedro with the lots of room line, introduced first transcendental spiral, and that spiral is important in quantum geometry and astronomy. It's not electromagnetic. And it's important because it is on the basis of Mercator projection that was proposed by Pedro. projection that is a straight line. So it is on the basis of two important concepts, calculus, that were just applied in the 17th century. The first is what nowadays we call the Euler approximation, but the question, just taking tangents. It means use for approximating orthograph by orthograph. So orthograph are the straight lines on the sphere, and we use small orthograph to approximate orthograph. So it's the Euler method, geometric, pre-geometric, and implementation that indicates what to do with classical geometry to technology. And again, the orthograph is again important in this result because by the end of the century, Edward Wright, in 1596, compute non-convective and was doing one of the first numerical integrations integrated in second. Just the same. This numerical method were integrated in integral at the second. So this is in fact another revolution before the revolution of the 17th century for the calculus that allowed Gauss to introduce this perspective as non-convective geometry. My second comment came from with the late 20th century. And the concept, this is the question behind the comment, is the shape of space. In fact, there is also the Thurston conjecture that was proved by Perelman, which Poincaré projected with one
simple case.
Simple case, exactly. And this is exactly the simple case concerning the shape of space question. Well, since Aristotle, the space was spherical. Now, we have the Poincaré and further conjecture that in fact only geometry in spherical volume will critical line there. And this raises this physical without question. We know that at our scale, the space is Euclidean and it's flat at our scale. At the cosmic scale, the geometry, is it spherical? It's my last question.
Thank you. Any further questions? There's another one there. Yeah.
I'm sorry. This was a very history of geometry, fascinating. But probably this wasn't what you did not show. But one thing I wonder is that why you did not cover modern development of non-convective geometry, in particular how they connect with these theories.
Well, that was my last part of lecture, but with, of course, yes, no, non. Well, I can say, maybe I will reply to Jose Francisco first. Yes, concerning this question of on the space, the shape of space, indeed, I mentioned only the solution of the Poincaré conjecture. Actually, there was a more ambitious structure, which is a more ambitious conjecture, which was due to William Thurston, which actually is dealing with the three-dimensional spaces, which have a local geometry, and the list of local geometries was proposed by Thurston. But he claimed that any three-dimensional space can be decomposed in pieces which belong to one of these six geometries. And with the techniques of Perelman, you can actually prove that. But actually, dimension 3 is the last dimension for which this is true. So starting with dimension 4, there are many, many more possibilities. And actually, it's even, I think it's even worse than that. That is, it's known that it's not countable. So you have, so it's much more open. Of course, you can describe some families with discrete numbers, but there are really many more degrees of freedom, if you want. So this is the difficulty. Now, concerning non-commutative geometry, of course, I could have developed that was part of my. Maybe I show you quickly just the slide I wanted to show on this, which is the slide on Alain Kohn. Yes. So this is Well, just to show you a picture I like very much of Alain Connes. So it's Alain Connes in front of the Lagrangian for the Standard Model, if you write it in the usual way. And of course, his claim is that if you use non-commutative geometry, all of a sudden this huge formula to describe the Lagrangian of the Standard Model of particle physics shrank a lot, because there are a number of constants which are built into the geometry and which relate things in ways which are interesting. So the motivation of Alain Connes was for non-commutative geometry was really physics. He really started from the early days of quantum mechanics and wanted to understand deeply the physics of matrices, Heidelberg and others, and wanted to have a mathematical description of that, which would be relevant. And he realized that the assumption that one usually makes, that functions on the space are commute with each other, of course, are inadequate to describe the key features of physics. And therefore, the space on which physics takes place is a space which has a richer structure, in the sense of a different kind of structure than the usual space. And therefore, you have to go to another type of geometry. The price you have to pay is very much, because first of all, you cannot anymore describe locally things by finitely many parameters. You need infinitely many parameters. And also you need a number of concepts that you have to introduce in order to make sense with the usual, for example, notion of volume, you need it, and what will replace the notion of volume? The notion of distance or metric, how do you define it? And so finally, it was quite remarkable, if you never had the opportunity, if you go back to the inaugural lecture of Connes at Collège de France, it's an amazing piece of, an amazing lecture, because more or less he describes what has been his work for 30 years, and a number of, he lists the number of questions which have to be solved. Now they have all been solved. And each time to solve this question, he's the one who proposed the turning point. Of course, many other people contributed, but it's quite remarkable. And so in particular, one thing for metric, which is very, shows the link, a very strong link with physics, is that it's really the proper conception is the fundamental solution of the Dirac operator, which provides the right notion for a metric. And so it shows that the inspiration of Connes has been step by step fully taken from physics, but of course that you have to do expensive mathematics, if you allow me the word expensive, that is hard and difficult mathematics. But now there was a conference in Shanghai in April, because Alain was turning 70, and which was an absolutely amazing conference. It's the first time I see this, that a number of people came to the conference with papers they had taken under their elbow for 1, 2, 3, 4 years, because they wanted to reserve it for announcing for the 70th conference of Alain Connes. And it was just an extraordinary moment. And many new things are happening. And the key point for this non-commutative geometry, which is of course the motivation of purely physics, but with it you can do very sophisticated number theory, which of course was not expected at all originally. So because of his approach, you can do both discrete spaces and continuous spaces. You can describe them with a similar context, which of course you cannot do with the traditional geometry I described, which is completely based on continuity. And you cannot do discrete structures. Of course, people have done discrete structures, which was the other part I skipped, but sorry, I don't want to talk more.
Thank you very much. I think we have to move on. I'd like to thank our speaker for his fantastic presentation. I also like to handle to you the diploma that proves that you were here and you were a member of our academy. Thank you very much indeed. Thank you very much indeed.
Thank you.
Now,
Thank you very much.